Okay, so here's the theorem we've been building up to, the residue theorem. Let me show you the setup. Let's say that f of z is a function which is analytic in the plane, except possibly at a certain number of poles, and those poles are isolated. So z1, z2, z3. So we might have a certain number of poles in the plane, but they're kind of spread out. Now let's say that we have a curve C in the plane, which does not intersect any of those poles. And let's say that the curve is oriented counterclockwise. Then here's what the residue theorem says. It says that the integral along C of f of z is going to equal 2 pi I times the sum of the residue of f at each of the poles which lies inside the curve C. So the sum is going to be over all the poles which are inside C. Now in this particular example, then since poles Z1 and Z4 are inside the curve, I would calculate the residue at Z1 and add the residue at Z3 and ignore the 2 points that were outside the curve. So let's work a fairly simple example, and then I can show you some examples which are more like what you'll be doing for your honors project. So let's say that our function f of z is equal to 1 over z squared minus 1. So in other words, 1 over z plus 1 times z minus 1. Then we see that this function has exactly 2 poles, one at positive 1 and one at negative 1. And let's find the integral of this function, 1 over z squared minus 1, over the curve C1 looks like this, say. Notice that C1 loops around 1, but it does not loop around negative 1. Well, by the residue theorem, I'm going to get 2 pi I times the sum of the residues, and there's only one, so times the residue of the function f of z at just the pole 1. So let's do a little bit of scratch work. Let's find out what the residue of this function is at 1. That's going to be the limit as z goes to 1 of z minus 1 multiplied by 1 over z plus 1, z minus 1. Those two factors cancel, and I get the limit as z goes to 1 of 1 over z plus 1, which is a half. So the residue at this pole is a half, so that means that my integral will be 2 pi I multiplied by a half. In other words, pi I. Now, imagine instead of C1, I took this curve C2. Let me change it so that C2 goes around both poles. Well, now, when I apply the residue theorem, I take 2 pi I times the sum of the residues at both of those 2 points. So I have to take the residue of f at 1 plus the residue of f at negative 1. Now we already calculated this first residue to equal 1/2. Let's do some scratch work to figure out what the residue is over here at negative 1. I'll take the limit as z goes to negative 1 of z plus 1 times f of z, which is 1 over z plus 1, z minus 1, this is the limit as z goes to negative 1 of 1 over z minus 1. And using direct substitution, I get negative 1/2. So the residue of the function at negative 1 is negative 1/2, which means that my integral is 2 pi I times 0, which is 0.